So without further ado, please welcome the speaker for your first session on AI on client PCs, TAP.
Thank you all. Great. Thanks for coming. Love every one of you. Thank you. Thank you. Yeah, whoop, whoop. Okay, let's kill the music. By the way, you probably did not notice, but that is a brand new generated AI-based version of the Intel Boing song. So that was actually done with a Meta LLM that is actually using an OpenVINO plugin to generate a continuation of the Intel Boing. So Gen AI is here. Okay. So my name is Tom Peterson. I'm a fellow in the computer graphics and AI team at Intel, and I'm going to be trying maybe what is the most difficult presentation of my life, because the AI is just really complicated. But what I'm going to try to do is give you a sense of what is Intel's strategy and how are we engaging with AI on a PC, and also what is the fundamental problem that we're trying to solve? Like, what is Gen AI? So my hope is to demystify Gen AI in general, which is a big ask, but also to help you understand why a multi-core strategy, which is what Intel's taking, allows you to really fulfill the promise of Gen AI on a PC. So to begin with, what's going on, right? There are a million different algorithms and a million different effects that are on the PC today, and more are coming. In this picture, I'm kind of showing you the dark blue are algorithms that are out today. Things like denoising, background removal, reconstruction, dynamic noise suppression. But the light blue ones are the really engaging ones. Those are the generative AI applications. Things like AI assistance, text to video, code debug, code generation, even brainwave generation, right? We're talking about fundamentally changing the characteristic of a PC. So you can tell that this is hugely important, not just to Intel, but to the entire ecosystem. So why a PC? Right, some people are saying AI is a cloud thing, it's not a PC thing. You could not be more wrong, actually. AI on a PC is important because of primarily three things. You can get lower latency on a PC because the inference is happening on a hardware accelerated platform, local. One example is CrowdStrike, which is a dynamic malware detection tool. It is running 73% faster now using NPU accelerated inference on the client PC. Another example is BufferZone, which is an anti-phishing package, which is now moved from the cloud to the client, reducing expenses by 91%. So that's kind of important. If you think about like a software application providing a service to somebody, your choices today for inference are run it in a data center where you're going to buy capacity and you're going to pay for that inference, or run it on the client where it's actually to the provider of the service free, because the platform is AI enabled, and if you exercise it, you can dramatically reduce costs. Lastly, privacy. I am so blown away by the types of AI clients that are emerging. All kinds of assistants. Maybe it's a medical assistant. Maybe it is a financial assistant. I read recently about a dating assistant. So imagine all of that technology uploaded to the cloud. Nobody wants to do that. As a matter of fact, 57% of surveyed users are very concerned about privacy, and that means all of this activity is going to happen on the client. Nobody is updating their financial profile to a random server. So let's talk about this multi-engine strategy. In 2024, it was roughly 25%, 40%, 35% of inference by engine today in 2024. So NPU 25%, GPU 40%, and CPU 35%. As we go forward to 2025, the interesting trend is there's a slight increase of movement to the NPU, there's a slight movement to the GPU, but overall, it stays multi-engine. I mean, that's kind of weird, right? Because I've heard that the NPU is going to take over everything. But the truth is, there are different applications, there's different workloads. If you have a low latency application, you can run that very well on the CPU, and you can very quickly, very easily give one-shot inferences using our CPU accelerated VNNI instructions at 5 tera ops on the CPU. If you're running a sort of like bursty workload that you're going to do a bunch of stuff. You're going to do a bunch of pictures or a bunch of text. Maybe you want to run it on the GPU, because the GPU is going to give you upwards of, I think, 76 teraops on Lunar Lake, which I'll talk about more in a little bit. And lastly, the MPU is more for things that are sustained, because you're going to be more power efficient. So you can do things like voice recognition or fingerprint recognition or face recognition constant on 24/7. You need a low power efficient engine. So there is a need for multi-engines to maximize the experience on PC. All right. So this is the first time in my life where it's gone from me selling something, like, hey, try this new effect, you're going to love it, trust me, to the pull for technology from the ecosystem is, you cannot deny it. There are over 350 different algorithms under development today with Intel's AE team, and 100 different ISVs that we're engaged with. So when you're talking about like the inexorable pull of the ecosystem, there is no further evidence than this, right? It is absolutely the biggest wave in PCs in recent memory. Okay, so that brings me to a really important point. PCs are, by their nature, somewhat contained, right? It's not a giant data server. It's not warehouses full of computers. It is a single computer. So how do you run these giant models on a PC? Today, there is different data widths that are shipping on AI inference models. Starting off, there's about 32% of existing models that are using FP32. FP32 stands for floating point 32. Think of it as the native width that you might train a model with. So up in the cloud, you're hanging out, there's gigajoules and megawatts, and you're creating a multi-billion parameter model. That's FP32. And that's pretty much the way it needs to be. But the truth is, that is not the model that gets deployed. When we're talking about models that are deployed, they get shrunk down, and the weights get compressed, and the model activations get compressed through a process that's called quantization. And what quantization does is it takes these giant FP32 models and it makes them smaller so that we can run them on a PC. Is everybody with me so far? Small models, good. Big models, natural. We got to quantize. So that brings us to the biggest thing, right? There's been an explosion in Gen AI. These are all just normal pictures taken of me. Maybe not. They are Gen AI pictures of me. I said, don't go too big, nothing too strong, but I don't know. I guess maybe I'm just naturally buff. But that's the biggest thing that's changed, right? AI is no longer inference. It's like generative. It's not like just classification. It's now creating content. And that all started in 2017. In 2017, there was a paper written out of Google called Attention is All You Need. Okay? And in that paper, they described something called a multi-headed attention thing and a transformer. Now that model is pictured here, has carried forward through time largely unchanged. That model, the transformer model, has been adopted by ChatGPT, by Facebook, by Google. It is the crux. It's like the magic bullet that has enabled the Gen AI revolution, okay? And I can tell you that what's happened is the models have gotten bigger, but they've stayed structurally very, very similar. The data types have changed. No longer is it like text to text. It's sort of like anything to anything. And it's really a hard concept to understand how that happens. But let me just assure you, it is all about attention, and it's all about transformers. So I'm in the next 10 minutes going to tell you everything you need to know about how this works. Okay, you're going to become AI experts in 10 minutes. Maybe. All right. All right, you ready? Here we go. I'm going to start simple. This is an orange. Okay? Now, when I think about an orange, I think about the characteristics of that orange. It might be sweet, might be sour, might be spicy, salty, whatever. Let's say I have 7 characteristics. I'm going to give it a score for every characteristic. Everybody understands that, right? It's just like, what is this thing? It's got different characteristics, no big deal. If I had a jalapeno, I might have the same characteristics, but they have different scores, right? Who's with me? Scores. Yeah, scores in the world of AI is an embedding. Okay, so what we're doing is we're taking this jalapeno, which is a word, and we're converting it into a set of characteristics that all have scores. And that is exactly what the process of embedding is doing. You're taking a word and you're converting it to a vector that has different values on each vector for each word. It's not that bad. This is going to be tough. Okay, it's not just 2 words, and it's not just 2 vectors. It's not 7 vectors. It's up to thousands of dimensions and tens of thousands of words. Okay, so imagine the same idea. You're taking a word and you're converting it to a vector, but the vector is now many, many, many different characteristics. If you actually plot that, you get pictures that look like this. Okay, now what I'm showing you here is a 2-dimensional projection of a 1,000-dimensional vector. That's a little hard to understand, but let's just say that in a local space, words that are describing a name tend to end up around each other. That means that somehow in this multi-dimensional space, meaning has been extracted. Like the dimensions represent characteristics that are real. It might be how much of a name are you? It could be how salty are you? It could be how sweet are you? So think about embeddings as converting from a word or a token to a vector. Is everybody with me so far? Any questions? Any questions? Okay. So I'm going to continue on, and I want to simplify this. So imagine just one word, chips. And chips has some multi-dimensional embedding, but I'm going to pretend it's just 2. And those 2 dimensions are vertical and horizontal. But those are semantic dimensions, so they represent something. And so chips is going to live up there at 9,9. So this is a real number, right? This is not a metaphor. Words are converted into vectors that have real numbers. And that's just the way it all works. By the way, these embeddings are created by looking at all the words that you can. Wikipedia, the entire Wikipedia. Looking at dictionaries, looking at code bases. These models have been trained with trillions of data sources that create these associations that have no human intervention. Right? There's no body who said, hey, let's create these 1,000 vectors and they mean this. That's all created from data. Okay? So let's imagine we got this 9,9. Nobody knows what it really means. But we know that the problem we have is that chips by itself is ambiguous. Right? Chips can mean a lot of different things. Chips can mean, of course, Intel chips. But chips can also mean potato chips. And chips can also mean chips of wood. So the problem we've always had in AI is how do you determine the meaning of a word? And you can't do that by the word alone. You need context. So if you think about it, if you have these sentences like chips in a laptop, you as a human know what kind of chip we're talking about, right? If you think about a bag of chips, you know, hey, that's like a chip of something. It's not a computer chip, it may be a potato chip. And similarly, you know, if you see chips next to garden, it probably means something related to wood. All right, so now we know context is important to understand an embedding. So what I want to do is try to find a way to change my embedding to include the context. So let's come back to this picture. Remember, chips is 9,9 off on the right. If I took each of the other words and plotted them in their embedded, they may be distributed in the same plane, right? These are just words that have been recognized in language, and they got their custom set of attributes that plot them in some multi-vector space. So what I want to do, hypothetically, is somehow I want to move chips towards laptop. Because I saw laptop in a sentence, I now know that my context, my true meaning, is not just what chips means. My true meaning is like chips in a laptop. So the way this vector space works is you literally add a little bit of laptop to the chips vector, and you get a new vector. And that vector now contains the context that differentiates that chip from every other chip. So how do we do it? Well, you have to imagine that this direction means I'm in electronics, right? If you're heading towards a laptop, you're kind of saying that vector represents the concept that you're in electronics. So that actually breaks down mathematically. If you think about it, while we were training this giant model, we created what I'm going to call attention matrices. Now, I will tell you right now, it's actually a lot more complicated than this. So don't pretend this is true, but it's a good metaphor. Okay, so we're creating an attention matrix, which tells you if I see chips, how important is laptop? Or if I see chips, how important is chips? So this matrix is telling me, based on all the language that I've seen, how much do I want to shift myself towards chips if I see it. So what we do is a multiplication. We take that 9 and we multiply it through there. We generate a new value for this matrix, and then we normalize and run a softmax. So the key thing is, to do this operation, you need a matrix multiply accelerator, you need a softmax, and you need a normalizer. Now after that, you're going to get a new embedding. So this new embedding, which is now going to be 7.4 by 9, actually moves chips from 9.9 to 7.4 by 9. And the hard part to understand is the number of dimensions is the same, the values have changed. Okay, and now those values represent the full context. It's not just chips, it's chips in a laptop. All right, so that is embedding, and that is attention, and that is the full set of fundamental concepts for where Gen AI comes from, right? There is no magic to Gen AI. Although before I started working on this, I thought that's just like crazy. But really at the end of the day, it's just about do a good embedding and then find a way to pull context into your embedded vector and then find a way to expand it. So it breaks down into 3 chunks. First, there is what we call an encoder. And the encoder takes all these information, this could be images or it could be text or video, and it goes through an encoding process, which is also called classification. And then classification generates a context-aware embedding. So think of it as all the classifiers that you've ever seen in the past. In your very first class of AI, they'll teach you about a cat detector or a dog detector, and you learn how to train a cat detector. That is garbage. All that stuff is thrown away. All those networks, nobody does them anymore because they only look at one word. Now you can have a cat that's not detected by the face of the cat. It's detected by the fact that there's a thing in a room with kittens, with a grandma or something, right? It's looking at the whole picture and generating the context to more accurately classify something. So this is the first step of the transformer. It's called encoding or classification. This is the model for the transformer on the encoder side. Remember I talked about embedding, then you go through that attention thing multiple times, then you're going to do some more feed-forward stuff, and you're going to output a context-aware embedding. The next step is a generation phase. And believe it or not, it is very similar to that other phase we talked about. You take your context-aware embedding. Remember we did all that attention stuff, and we did that normalization. Now we've got a vector that we're going to pass through another network that's doing very similar stuff. It's doing that multi-headed attention thing, going through a bunch of softmax layers, eventually generating an output. And the output can be anything. It could be an image, it could be words, it could be a face, it could be brainwaves. So this is the fundamental output step. If you add these two together, you'll see the multi-headed network looks very, very, very similar, right? And lastly, if you put these two things together, you will get translation. So I'm taking an input, sound, thought, video, images, and then I'm generating a context-aware embedded vector, and then I'm taking that vector into the output to generate something. And this is word to text, text to speech, speech to word, and this is what we really think about as Gen AI. All right, so that was a 10-minute description of how all this works. This is the final network where you kind of say input embedding, do forwarding stuff, pass it down to your decoder, and boom, I'm going to get a happy face. So you might ask yourself, why am I talking about this? Because it's kind of complicated. But it's critical because, first of all, it's the fundamental architecture of Gen AI. You've all heard about Gen AI. Haven't you wondered about what's going on? It is so complicated, but at the end of the day, it breaks down into 3 pieces: embedding, encoding, and decoding. Lastly, I hope you get the sense that you need hardware acceleration, because I mentioned how there's this multiplication in the middle. You need a softmax, you need basically a normalization layer. All of that needs to be hardware accelerated, because the truth is these networks that we're talking about are billions of weights, 14 billion, 18 billion, 23 billion weights. And think about how would you do that calculation without acceleration? It's impossible. Lastly, you should know we need compression, okay? Because compression is taking billions of weights and moving them to something much, much smaller that'll run on a PC. And I'm happy to say Intel has been involved in all of this for a long time. Okay, so before we continue, I would like to show you this in action, but let me tell you one more thing first. The key concept I have not talked about is something called RAG. RAG is context augmentation. It's basically where you can take additional information and add it to these models without retraining. And what it actually does is sort of does an embedding and prepends itself to the prompt. You don't need to know about the details, but let's just say RAG allows you to take local information and add it to a pre-trained language model. So Craig, let's pull up the demo. This is the Phi 3 LLM, so what are we looking at?
So this one is Phi is a brand new class of LLM model that Microsoft has coined for its open source introduction of Phi 1, and they're calling it the SLM, which is a small language model. So imagine a model that is below 7 billion parameters, something that's easily workable on small memory footprints, similar to what I would have locally on the machine on an AI PC here. And so Phi has an excellent sort of capability and pedigree for physics, mathematics, and coding. And it also adds reason and language understanding. So it doesn't have the entire human knowledge base like a ChatGPT or something like that, just very trimmed down set of model to be able to run very, very fast in these type of capabilities. So let me give you an example of how this works here. So really quickly, write me a function in Python. And just like that, we have our base. I've used speech or speech to text to be able to enter our prompt here. And that's actually being used by Whisper in order to enable that feature in our Phi 3 model here.
Okay,
and
so I want to stop it right there. The Whisper is, it's a transformer. It's speech to text. It's an open source model, and it is hardware accelerated on the NPU right now.
That's correct. And so we're actually looking at multiple models here accelerated in different areas across the XPU. And so we're going to be talking about, when we talk about RAG, a good portion of that indexing is used in CPU, and then the model itself for the LLM is being accelerated by our GPU, and that Whisper additional capability is on NPU. So a great example of one model use case going across all of our XPU targets.
That's really cool. Now, is the platform you're running on, is that Lunar Lake or is that Meteor Lake?
This one is currently on Meteor Lake.
Meteor Lake.
So showing off all of the great coding pedigree that we've put up to this so far,
cool.
and then can't wait to show us some more
so
great
on that
examples.
Meteor Lake, then when we're accelerated on the GPU, we're using an accelerated instruction called DP4A, which allows us to kind of break up our vector unit into multiple 8-bit chunks and targeted at accelerating AI. So why don't we try another example here?
Yeah, of course. So we can go ahead and take a look, but let's go ahead and, did you have an example that you wanted to take a look at?
Yes, I would like to know, and I've been thinking about this, I want to know what should I do late at night in Taipei? I don't know. I think it's going to be PG, right?
Here we are with a live demo. We are absolutely
Anything can
going
happen.
to see.
Get ready to go to screen. Go to
backup.
Go to backup.
So what should I do late night in Taipei? It's recognized Taipei. That's great.
Taipei 101. I love it. Oh, Roe Street? Is that what you were talking about? Rao? Okay, cool.
Rao
Night Market?
was
Is
just
that
there the other night.
Snake Alley? That's great. So it knows about what I should do in Taipei late at night. Okay, great. Now let's talk about RAG. Remember how I mentioned that we can augment this database without retraining it? It happens really, really quick. So Craig, why don't we show before RAG? Ask a question that we think it won't know.
Yeah, we'll give it one that causes the model to break a little bit. So I'm going to ask it about how many SKUs that we currently have in our Intel Core Ultra H processor.
It's a question that is on the top of everybody's mind.
Yeah, and so as it's going through the answer piece that you're showing here, it's actually, we've tricked it to do a little bit of hallucination on that piece, and also because we're attacking some of its vulnerabilities as far as if you look at the very last sentence, it's taking a look at the knowledge cutoff date and says, this is the best answer that I could come up with based on the limited number of information that I have.
Yeah.
And so, and that's a good thing for us to know, is that all models, large LLMs, have a training cutoff date where that's the last date that they're going to be able to know.
Right, but why don't we do the RAG? Hop in.
Well, now RAG, let's add some information into this model really quickly. So with RAG, or retrieval augmented generation, I'm going to add a document here. And so this is is an internal Intel Meteor Lake document, so it's nice to keep this private. I don't have to open this. These bits never leave my machine here.
And that augmentation just ran on the CPU, is that correct?
That is correct.
Okay.
And now I'm going to go ahead and we're just going to ask it the exact same question based on this new retrieval that we have with the document. And Force is correct.
Excellent.
Force is correct.
Thank God.
Yeah.
Thank
so
God.
now we have a working demo, and to prove it to everyone here, also a great aspect of Phi 3 that you can enable is we can actually take a look at the transparent answer of where it's gleaned that information. And
Very
so
cool.
we actually get the retrieved documents there to the exact paragraph and document that we retrieve that from. So great way to add new superpowers to your LLM.
Great, I really appreciate that, Craig. Great demo. It showed GPU, it showed NPU, and it showed CPU. So I think it's sort of an example right now of why multi-engine is important, because workloads are different, and different workloads map better to different hardware. So let's summarize. Come back to slides, please. That just showed you a high-performance LLM running on a client. It was less than 1 second for the first token, which is a normal performance measure of LLMs, like how quickly can I get an answer. It was more than 25 words per second, so if you think of it as typing those words together, that's faster than a human can read. So think of it as these LLMs are now so fast and so powerful running quantized models on the GPU and CPU that people can't keep up. And lastly, RAG enablement. RAG enablement on a PC is going to open up the door for all kinds of very, very personalized services. Okay, and that is a really interesting opportunity for everybody. Moving forward, we talked about how we build these models right up in the clouds, big giant supercomputers. I talked a little bit about the fact that those models need to be optimized before we can run them, right? They're too big, too many parameters. Got to be squozen down, and I'll talk about that in a little bit. And then the last step is you have to be able to execute it, right? A model's no good if you can't run it. So the hardware acceleration software stack is critical, okay? So let's talk through these in order. First of all, dealing with quantization. Obviously, Intel supports the Microsoft Olive kind of package of quantization for the Windows platform. We also have an Intel neural compressor, which actually bundles up a tremendous amount of algorithmic work for compression. And lastly, there's a neural network compression framework from Intel that is actually embedded into our OpenVINO software platform. Okay, so when it comes to compression, we know there's a lot of work to do, there's a lot of algorithms that need to be processed. And I want to kind of walk you through a little bit about what's going on with compression. First of all, you need these things, right? You can't run giant models on a PC. You need lower latency, higher throughput, lower storage, lower power, and lower memory, and that's the benefit of compression or quantization. Let me show you this in numbers. This is showing you a Llama 13 billion parameter model and a 7 billion parameter model. And if you go from FP32 to FP16 to N4, guess what? Division works. And you cut the model size in half, and it comes down pretty nicely linearly. Same with the Llama 7 billion. So the point is, if you can find out how to shrink these parameters and how to shrink the activations, things will get a lot faster. Let's talk about the first step here. If you also are able to shrink those models, you get higher performance. So it's not just about lower footprint, it's also about higher performance, primarily because these language models are bandwidth limited. Most of the time, especially for second token, third token, it's about bringing in the weights and doing a computation. It's not about the actual mathematics. All right. Now this is another view of quantization. I'm showing you many different models here, Llama 3 going up. This is, say, as an example, a 13 billion parameter Llama 3 model. And each one of these dots represents increasing amounts of quantization. So you can actually see this as a log scale. So you're basically cutting it down by factors of 2 every time. But the odd part is that, or not the odd part, but kind of the consequence of this is something called perplexity. Okay, perplexity is a critical thing to understand. And what perplexity is talking about is how confused is your model. So as you're shrinking down the weights, your model is becoming more confused, which is not great. You'd prefer your model to not be perplexed. Perplexed is actually a measure of the output layer and how 50-50 it is. Like if I could pick any word equally, that's heavily perplexed. But if it's selected one word, that's low perplexity. And you'll find that models that have high perplexity spew gibberish, right? So it's not sufficient to talk about performance, right? Because a lot of people are talking about tokens per second. You can see as the model shrinks, performance goes up, but so does perplexity. So you have to consider both of those at the same time. All right, so quantization. I'm going to start on this side. You can see that in the beginning, all your weights were FP32 because they were trained in a giant gajillion data center somewhere in space. Okay, now the activations, which is the mathematics of the model, are all FP32 because that's the way models work on GPUs today. What you want to do is make it smaller. So this is something like I would probably do, and this is the technique that a lot of people do, which is called weight quantization. And what you do is you apply a nearest neighbor algorithm to basically say, drop the big numbers. Like if it's saying 13,123.66555, whatever, drop the digits, and let's just call it an int8 representation of that using the nearest integer to the floating point value. That shrinks the weights by a factor of 4. And that is actually really awesome, and it often works very well. The problem is this tends to increase perplexity quite a bit, right? Because there's no real validation, there's no back off. So this quantization technology has advanced over the years dramatically. Now, the next step would be called post-training quantization. In this technique, what we're doing is sort of trying to lower the weights, but then we're checking whether perplexity jumps. And if perplexity jumps, we'll back it off. So think of it as you're trying to push things down smaller, but you're checking with a calibration data set. And that allows us to selectively have weights that are smaller or bigger. That is what leads to these mixed precision models. So that's another key thing you should take away. Models are generally not going to be FP32 or FP16 or int8 or int4. They're going to be a mix, right? And they're going to be a mix because they are quantized. All right, so my last major topic is the delivery of these tools. So I talked about a few technologies. We mentioned that we support Olive. We have our own tools. One is OpenVINO and one is a standalone set. Today we're announcing that we are contributing Intel Neural Compressor, which is that collection of quantization algorithms, into the Onyx runtime open source project, right? So all of this quantization technology that we've been working on is now part of Onyx, which is really, really cool. Intel loves open source. Okay, now the reason that's critical is because we've got to deploy these things. We've got to use the leverage of the ecosystem to get these AI models into the hands of users. So I'll tell you how that works. Here's our software stack. There's really three main ways that AI gets accelerated in a PC. One is OpenVINO, which is an application developer, works with Intel, and they will usually get the highest performance acceleration on any Intel hardware. But it is not exactly multi-vendor, right? This is pretty much an Intel thing. Onyx Runtime is the default Windows API. So imagine if you're using Windows and you're writing an AI model, you could easily use the Onyx API. This is an open standard for how to define models and sort of weight characteristics. This runs on top of something called an OpenVINO EP, which is an execution provider. So we make a little chunk of OpenVINO that works with Onyx to accelerate AI when it's on an Intel platform. The last method is the web, right? So if you're a web developer, you also want to access inference. So now there's web APIs like TensorFlow Lite and others that they can directly access in their web application. All of that stuff flows through the stacks and lands on one of the three different hardware-enabled GPU accelerator, CPU accelerator, or NPU. So to better understand this, I think a few examples help. Okay, example number one will be Zoom. Okay, so Zoom integrates OpenVINO. So we've worked with Zoom for a long time. OpenVINO is their application API. It goes through our stack, it hits our XPU plugin, and depending on the effect, can target either the CPU, the GPU, or the NPU. It's a really cool example of how a multi-engine platform allows, effectively application developers to pick the right engine for the right effect. Another example is Office. Microsoft Office, runs directly using the Onyx runtime. And this is their standard, it's an open standard, which is great. In this case, we're going to say they choose to accelerate onto the CPU. So they're going to go through a library called MLAS. MLAS is effectively a mathematics library that is targeted at certain Intel CPUs for fast matrix operations and the like. So think of MLAS as, if I'm going to target the CPU, I've got a library of accelerated functions. Lastly, or third, we've got Windows AI. So Windows is a collection of interfaces. Some are called things like Copilot, some are called MEP. These are all effects and AI services that they're making available very soon to users. That goes through the Onyx runtime. In this case, the Onyx runtime will roll through OpenVINO, the execution provider for the Intel platform, and it'll land most likely on the MPU given Windows software architecture. Are you with me so far? It's all making a little bit of sense? Multi-platform, multi-engine, the right tool for the right problem, all that good stuff. Lastly, Khan Academy. So I didn't normally think of Khan Academy as a target for AI on a PC. They actually use the web interface, and they're using basically a voice to text to drive their web experience. So in that case, it goes through TensorFlow Lite, through a platform called WebMN, which goes through DirectML, driving through our stack down to both the MPU and the GPU. Okay, lastly, PyTorch is everywhere. Okay, so PyTorch needs to know a little bit about what your platform is. So there's a platform extension called IPEX, which is the Intel extension for PyTorch available today. It allows people to code natively to accelerate on Intel platforms, meaning GPU or CPU or MPU, all enabled through IPEX. Okay, so today I want to also bring your attention to Intel's attempt to accelerate all this adoption. We're making available an AI PC development kit based on Lunar Lake. It's early access, development ready, and will scale performance. So it's got a Lunar Lake, it's got a nice little kind of box. It's available for software devs and ISVs. If you're looking to run a large language model on a PC, we want to make it easy. Okay, so with that, let me conclude. Intel has a multi-engine strategy for AI, right? The first engine is the CPU. The CPU is either a P-core or an E-core. It has VNNI instructions and AMX instructions, which are vector accelerators. So you can map matrix multiply and softmax directly to their native instructions on the CPU. That will deliver today around 5 teraops peak. So if you think about it, this is perfect for I don't want to learn any new APIs. I just want to write some simple inference stuff, and I can do it with basically no context swaps. And it's just part of my program like everything else. The second engine is the GPU. On Lunar Lake, I'm going to tell you about XE2. XE2 is our brand new GPU architecture, and it is driving Lunar Lake. And I'll be going into great detail about what XE2 is in the XE2 kind of GPU on Lunar Lake section later today or tomorrow morning. In that architecture, I'll tell you about XMX, which is now up and down our stack. So Lunar Lake includes XMX, which is a systolic array built into our GPU, delivering around 67 peak teraops. Okay, so that is a very heavyweight AI accelerator on the GPU, and it comes with all those software stacks that I talked about. So it's very cool. Lastly, we have a brand new MPU, the MPU4 that Darren Crew is going to tell you all about in our next section. It is up to 2x the power efficiency and delivers 48 peak teraops. So if you think about Lunar Lake, think about AI PC, designed for AI, multi-engine, ready to roll, right? We've got many different things to pick from, up to 120 peak tops on the total platform, right? 76 from the GPU, 48 from the MPU, and 5 from the CPU. I am on time. That concludes me.